Hi, we're the Comrades, and in this video, we will present the question generation and answering system that we developed for 11411 natural language processing. Our system takes as input a text file extracted from a Wikipedia article, generates fluent questions from it, and generates answers to arbitrary questions about the article. Our system has three main components: pre-processing, question generation, and question answering. We will go through these three systems in that order. In the pre-processing step, we employ the Spacy Python library to do tokenization, POS tagging, and named entity recognition. We also added two pipelines to expand Spacy's functionality. The neural co-ref pipeline allows us to resolve multiple references in the text to the same entity, and the Berkeley neural parser adds constituency parsing. Once the text is pre-processed, it is passed to our question generation module. The module first scans the article, and using the constituency parser, extracts all simple predicate sentences. It defines a simple predicate sentence as a sentence having the form S goes to NP-VP, VP goes to VNP, with each noun constituent having a limited internal structure to ensure that there are no relative clauses that could complicate question generation. After the predicates are found, they are further filtered to predicates with only appropriate length noun phrases. For example, the sentence, "I shot an elephant in my pajamas," would be extracted, since it conforms to the grammar requirements. The sentence, "Chatterer said Buster thought the tree was tall," however, would not pass, because the highest level VP has another sentence as a constituent. Using these found predicates, we generate two separate kinds of questions, WH and binary questions. For WH questions, we first query the sentence to subject using named entity recognition to get the correct WH word. This query is expanded using coreference resolution, allowing us to generate questions from predicates with pronoun subjects. For example, if the subject is a person like Luka Doncic, the young goat, or he, we would use who. If it is a place like Times Square, we would use where. This step allows us to generate many more questions because we can include every sentence that co-refers to a named entity, including ones with pronominal subjects. Once we have the WH word, there are two cases. If the verb of the predicate is some form of to be, we will form a question by concatenating the WH word, the predicate's verb, and the subject. For example, the sentence, "Luka Doncic is a Slovenian professional basketball player," would generate the question, "Who is Luka Doncic?" For all other verbs, including to be, we will generate a question by replacing the predicate subject with the corresponding WH word, and concatenating the WH word and the verb phrase. For example, the sentence, "Luka Doncic gets buckets," would return the question, "Who gets buckets?" For binary questions, if the verb's lemma is to be, we create the question by moving the verb to the front of the sentence and using named entity recognition to get the entity of any co-reference subjects. So for the example, he is a Slovenian professional basketball player, we would generate the question, "Is Luka Doncic a Slovenian professional basketball player?" If the verb's lemma is not to be, we prepend the appropriate form of does to the front of the sentence and replace the verb with its lemmatized form to create our question. For example, "The young star got buckets," would return the question, "Did Luka Doncic get buckets?" For both of these question types, we also generate a false question by simply adding the word not before the object in the to be case and before the verb otherwise. Once we've generated all our questions, we place them in bins based on their type and create queues by ranking them within those bins. Our ranking criteria prefer questions with resolved name entities, especially those with large number of co-references, because we assume those to be focal points of the article. We also give an extra boost to questions that have the main reference of an entity cluster, because that's usually the first introduction of it where they'll give an existential clause. We penalize questions that are longer or shorter than 10 words to keep an ideal length, and discard any questions that have pronouns in them. With our queues ordered by rank, we pick alternatively from the queues so we get an equal number of WH and binary questions. Once a question is picked, we move it to the back of the queue to allow it to be recycled in case we can't generate enough questions. Now we will explore the question answering part of our system. The way we attacked this task was to match a given question to another question first, rather than just attempting to find an answer in the text directly. We do this by running our question generation module on the article, which will return a set of questions and associated predefined answers. We first use Spacy vector similarity to attempt to find a suitable match with a high similarity score. If a match is found, we return the correct answer. Otherwise, we default to a direct answer creation system. This system is advantageous to any system running direct answer creation because it is easier to match two questions than to mine for answers in a document. It also ensures that if a match is found, the answers are both semantically and syntactically correct. Here we have a graphic that depicts the logic behind our system. First seeing if there is a match in our questions with vector similarity and then returning that input, and if not, defaulting to our direct answer creation system that we will discuss later in the video. Now, we will quickly explain the logic behind question generation for answer creation. For example, if the article is about a Togepi Pokemon, we may expect to see this question given to the system. After running the question generator on the article, this question and associated answer may be in the set of generated questions. After performing a Spacy similarity function on the two questions, we get a relatively high similarity score of around 0.92, indicating that the two questions probably are asking something similar. We then return the correct answer without ever needing to mine the article for the answer. Looking back at our original graphic, the question arises, what if we can't find a suitable question to match to? If our robust question matching system does not find an accurate match, then we will default to direct answer retrieval.
First, we use our classified questions and we case on each type of question. Using spacey vector similarity between the sentences in the corpus and our question, we look only at the most similar sentence for the question. After this, we tag the tokens in each sentence and use common heuristics to return the correct token. This approach also has the advantage of always returning the correct type of token. In the first example, our vector similarity will return the matched sentence from all sentences in the corpus. We first remove all matching words, as the answer to a question won't be in the question. Then for where questions, we look for a tag location in the text and return this. In the second example, we again return the matched sentence and remove all matching words. Then we look at the dependency class for who, which returns n subject. We match this to the only word that is also tagged by n subject, which is Cynthia. Here, we see an updated graphic of our question answering system that includes dependency parsing and POS tagging for when the quickest part of our implementation is not sufficient. This progression through the question answering process allows for the quickest solution to be found, while also being able to handle unfamiliar inputs with a more comprehensive solution. This, paired with our question generating system, helps our system to be the best one out there. Thanks for watching our project video from Team Tongzhimen.